Hi, I'm Sharmine. Today I'll be explaining about IEEE Green Book. IEEE Green Book is a recommendation practice for grounding of industrial and commercial power system.
So system grounding. System grounding, grounding of an electrical system is a decision that must be faced by most engineers. Grounding is generally recommended, but there is 3 exceptions where you can actually let loose about this grounding. System standards, which is the location within the power system, individual generator characteristic, and manufacturing process requirement.
The purpose of system grounding. System grounding is the intentional connection to ground of a phase or neutral conductor for the purpose of controlling the voltage with respect to earth or ground within predictable limits and providing for a flow of current that will allow detection of an unwanted connection between system conductor and ground. Such detection may then initiate operation of automatic device to remove the source of voltage from this conductor. In an ungrounded system, there is no intentional connection between the system conductor to ground. However, as shown as in this figure, there always exists a capacitive coupling between one system conductor and another, and also between the system conductor and ground. Consequently, the so-called ungrounded is in reality capacitance, grounded system, by virtue of the distributed capacitance from the system conductor to ground. Since the capacitance between phases has a little effect on the grounding characteristic of the system, it will be disregarded. For simplicity, the distributed capacitive reactant to ground is assumed to be balanced. In an unfaulted condition, with balanced three-phase voltage applied to the lines, the capacitive charging current in phase will be equal and displaced 120 degrees from one another. The phase voltage to ground will also be equal and displaced 120 degrees from one another. The vector relation are shown in part 1, picture 1. Since the neutral of the distributed capacitance is at earth potential, it follows the neutral of the transformer is also at earth potential, being held there by the capacitance to ground. If one of the system conductor, phase C for an example, fault to ground, current flow through the capacitance to ground will cease, since no potential difference across it now exists. The voltage across the remaining two distributed capacitor will, however, increase from line to neutral to line to line. The capacitive charging current in the two unfaulted phases will therefore increase by the square root of 3, as shown as the picture number 2. The line ground current are no longer 120 degree, but 60 degree apart. Hence, the vectorial sum of the capacitive charging current to ground is no longer 0, but 3 times the original charging current per phase. The fault current flowing from the faulted conductor to ground leads the original line to neutral voltage by approximately 90 degrees. In an ungrounded system, it is possible for disruptive transient overvoltage to occur throughout the system during restriking ground fault. This overvoltage can be several times normal in magnitude, result from a resonant condition being established between inductive reactance of the system and distribute capacitive to ground. This phenomena is discussed in detail by Beeman. Experience has proven that this overvoltage may cause failure in insulation at multiple locations in the system, particularly at motor. Transient overvoltage from restriking ground fault are the main reason why ungrounded systems are no longer recommended, and grounded systems of some form are the predominant choice. To reduce the transient overvoltage during restriking ground fault, one should ground the system using either solid or impedance grounding as indicated in this picture. Various detection schemes are used to detect the presence of single line to ground fault. The simplest scheme to employ these three light bulbs, each range connected to line voltage and ground. Under normal operation, entry bulb are illuminated with low equal intensity. When the single line to ground fault occur, the bulb connected to the fault phase extinguish. In the resistant grounded system, the neutral of the transformer or generator is connected to ground through a resistor. A typical resistor grounded system, as commonly installed, the resistor has considerably higher ohmic magnitude than the system reactance at resistor location. Consequently, the line to ground fault current is primarily limited to the resistor itself. Low resistance grounding is designed to limit ground fault current to a range between 100 ampere to 1000 ampere, with 400 ampere being typical. A neutral resistor since the combined effect of charging current and the system source impedance will affect the ground current value less than 0.5% in the typical range of utilities supply system, it is permissible to ignore this effect in calculating ground fault resistance value. The general practice is to consider that the full system line to neutral voltage appear across the grounding resistor. Only in this case of systems supplied by small generator should departure from this general practice to be considered. One method of detecting the presence of ground fault is by using overcurrent relay 51G. This method, when a ground fault is occur, the neutral potential is raised to approximately line to neutral voltage, resulting a current flow through resistor. A typical turn ratio for the current transformer is indicated. Upon indication, the ground fault current has occurred, action would be initiated to disconnect the transformer to secondary circuit. Since it is the intent that the ground fault current supplied by low resistance grounding be promptly and automatically cleared by protective relaying, the grounding resistor can be rated for intermittent duty. Normal practice is to rate it for 10 seconds or 30 seconds, depending the degree of security appropriate to the application. In cases of fault that are not or cannot be disconnected by secondary breaker, the ability for prompt and automatic disconnection of the primary source is required. Low resistance grounding find application in medium voltage of 15 kilowatt and below, particularly where large rotating machinery is used. By limiting the ground fault current to 100 of ampere instead of 1000 of ampere, damage to expensive equipment is reduced. A special application of low resistance grounding is also mandated in mining systems supplying portable equipment, drilling cables. Both high and low resistance grounding are designed to limit transient overvoltage to safer limit. Let's say 250% of normal. Reactant grounding. The term reactance grounding describes the case in which reactor is connected between the system neutral and ground. Since the ground fault that may flow in the reactant grounded system is a function of the neutral reactance, the magnitude of the ground fault current is often used as a criterion for describing the degree of grounding. It is considerably higher than the level of fault current desirable in a low resistance grounded system. Therefore, reactant grounding is not usually considered as an alternative to low resistance grounding. Solid grounding is recommended for low voltage system, which is 600 volt below, where automatic isolation of the faulted circuit can be tolerated, or where capabilities is lacking to isolate the ground in a high resistance grounded system. It also are recommended for medium or high voltage system, which is above 15 kilowatt, in order to permit the use of equipment with insulation level ground rated for less than line-to-line voltage. And also, medium or high voltage application, where the desire for a higher magnitude of ground fault current in order to be able to provide selective ground fault detection on lengthy distribution feeder outweigh, outweigh concern about arc flash and potential gradient as personal hazard to a workplace setting. The best way for the system neutral for grounding purpose in three-phase system is to use source transformer or generator with Y connector. Location of system grounding point for transformer, we need two requirements. The transformer winding at the voltage where a ground is desired must be connected in Y design. The impedance of transformer to ground fault current must be significantly lower than the impedance of the connection between the neutral and third, such that the neutral impedance governs the selection of grounding mode. The generator may be required by standard to withstand less than 10 per unit short circuit, whereas transformer may be required to withstand 25 per unit current. The generator may be capable of withstanding less than 25% of the heating effect of this current as compared to the transformer. If the current is unbalanced, this capability may be reduced less than 10% of the transformer capabilities. Unlike the transformer, the three sequence reactor of the generator are not equal. The zero sequence reactant has lower value, and the positive sequence reactance varies as a function of time. According to NEMA, the generator is required to withstand only the three-phase current level unless it is otherwise specified. Also, NEMA states that the negative sequence current thermal withstance limit is a product of time in seconds, and the square per unit negative sequence current equaling 40. With a solidly grounded neutral, the steady-state ground fault current will be about 8 times of that full load current, while the steady-state three-phase fault current is 3 times full load current. But because of the negative sequence content of the ground fault current, the generator has less thermal withstance capability than it would be for three-phase fault. Generator produce slightly sinusoidal voltage because of the saturation and imperfect winding and flux distribution. Industrial generator therefore produce odd harmonic voltage, with harmonic voltage being as much as 10%. This harmonic voltage can cause heating from circulating current in closed loop. This is why most industrial generators have their own internal winding connected to Y rather than delta. The third harmonic voltage produced in the generator winding are in phase and additive. This would be the cause of the harmonic current to circulate within the delta connected winding. The circulation current would create additional heating in the generator, thereby reducing some of its thermal capacity. Generators that operate in the delta connection allow for this in their design. NEMA places a requirement on design of synchronous generator that winding shall be braces to withstand the mechanical force resulting a voltage three-phase short circuit at the machine terminal. Generator phase current to ground can actually exceed this three-phase value, causing possible machine damage. Some of the general purpose DC lighting and system exist in industrial and commercial installation. With this system, they do exist. They should be solidly grounded accordance to NEC. Station battery system. Station battery system are used in power control source for switch gear and process control improvement. In addition, the station battery may use for emergency lighting or other emergency power requirements such as bearing loop oil pumps for rotating machinery or valve actuator for critical valve. The battery system are operated ungrounded and usually have ground detector. The ground detector may be lamp, wall meter, or alarm relay. The ground detector is usually furnished as an optional part of the battery charger. Electrochemical system. Electrochemical system, electrochemical cell line are used for the separate of chemical metal from raw material or from material produced as an intermediate step in the process. Additionally, electrochemical cell lines may be used to provide corrosion and abrasive resistance to change a surface appearance. Typical uses are the production of chlorine and sodium chloride and the refining of aluminium, magnesium, and copper. In general, the cells are connected in series parallel configuration and are supplied from rectifier to DC generator. Voltage may be as high as 1200 volt and the current as high as 400 kiloampere. Higher currents are found in chlorine industry and higher voltage are found in aluminium industry. Electrochemical lines are generally operated ungrounded. Line to ground voltage are monitored so that ground may be detected and removed before a second ground occurs. Some higher voltage DC port lines in aluminium smelter may be grounded through a fuse, which is monitored. The fuse blow on the first occurrence of the ground fault and the alarm is sound. Operator and maintenance personnel ordinary work of electrochemical system while the system is energized. Safety information may be found in IEEE standard 143 photovoltaic system. NEC addressing the grounding of solar photovoltaic system. For a photovoltaic power source, the NEC required that one conductor of a two-wire DC system over 50 volt and the neutral conductor of three-wire DC system be grounded. An exception states that other methods that accomplish equivalent the system protection and that utilize equipment listed and identified for the use shall be permitted. The NEC states that the direct current circuit grounding connection shall be made at any single point on the photovoltaic output system. Surge arrestor are used in DC transit system. For the same reason, surge arrestor are used in AC system. To clamp a voltage rise at a level the equipment can withstand and to dissipate the energy in the voltage peak. Care and planning are required in the selection of location of DC arrestor. Consideration are the following: length of leads, proximity to protect equipment, isolation from AC ground grid, especially if the AC primary is not solidly grounded, isolation to ground leads from ungrounded structure. Okay, we are here in chapter 2, which is equipment grounding. The term equipment grounding includes the equipment grounding conductor and refers to the interconnection bonding and grounding of the non-electrical metallic element of the system. The term covered in chapter 1 may include and is the part of power distribution system. The need for an EGC exists for high impedance, low impedance, and effectively grounded system as well as ungrounded system. Example of component of the equipment grounding system are metallic raceway, motor frame, equipment enclosure, and the grounding conductor wire. The requirement of the equipment grounding are expressly specified in the National Electrical Code, which is NEC, as follows. Conductive material enclosing electrical conductor or equipment shall be connected to earth as so to limit the voltage to ground on this material. Where the electrical system is required to be grounded, this material shall be connected together and to supply system grounded connector. Where the electrical system is not solidly grounded, this material shall be connected together in a manner that establishes an effective path for fault current. Electrical conductive material that are likely to become energized shall be bonded to the supply system ground conductor, or in the case of ungrounded electrical system, to the electrical system grounded equipment in a manner that establishes an effective path for fault current. Electric shock injuries result from contact with metallic components that are energized, whether it is intentionally or unintentionally. Effective equipment grounding practice can minimize these personal injuries. Safety consideration required that the level of shock hazard voltage to be minimized as much as possible to less hazarded level. equipment grounding system should do this by forming a low impedance part to ground. Thermal capabilities. Grounding conductor must also function to conduct the available ground fault current without excessive temperature rise or arcing. The use of large cross-section grounding conductor is not enough. All the part of the fault circuit, including the termination of other parts, should be capable of carrying the fault current without distress. Equipment grounding as influenced by the type of use, there is 5. Outdoor open frame substation, outdoor unit substation, outdoor portable heavy duty equipment, and interior wiring system, interior unit substation, and switching center. Okay, outdoor open frame substation. Outdoor open frame substation. The distributed nature of typical outdoor open frame substation presents some of the most perplexing equipment grounding problem to be found anywhere. It is common that various pieces of major apparatus will be found as an island installation within the substation area. For any single equipment item, the voltage stress imposed in the insulation system will be determined by the voltage difference between its electrical terminal and the frame, or the metal case that encloses its active part. The magnitude of the electric shock exposure to an operating or maintenance person within the substation area will be a function of a voltage difference between the ground surface on which this person stands and the metal that the person normally touch. The magnitude of electric shock voltage exposure to a person approaching and closing fence will depend on the character of the surface voltage gradient contour adjacent to the fence on the outside of the substation area. It is very important to avoid a metallic extension from the station structure to some point outside of the fence area, which is exposed to contact by person or animal. Such that extension might take a form of a water pipe, an air pipe, messenger cable, seemingly having no electrical function. What it does do is convey the potential of the station ground mat to the far end of the metal extension. The surface potential drop off fairly rapidly as one moves away from the boundary fence. The 50% of voltage contour will reach in a short distance away from a small station and in a longer separation distance from a larger station. Even in a fairly large station, will display 50% drop of a surface potential within 3 meters. Thus, it would be entirely possible for someone standing on earth touching pipe extension from the station structure only 3 meters away from the enclosing fence to be subject to an electric shock voltage of 50% of the ground mat voltage of the station. A station ground mat voltage of 5,000 watt is not at all unusual for station operating in 4.16 kV to 33 kV range. Unit substation. While the functional objective remain unchanged, the concentration of apparatus item into single metal enclosing package greatly simplify the equipment grounding system plan. Within the problem of avoiding dangerous electric shock voltage exposure to person in proximity to the enclosing fence involve the same consideration as in the case of open frame substation. Within the confines of many industrial plants, impedance grounding is used to limit the level of ground fault current. Being a common value of low impedance grounding, this reduces the voltage gradient around the substation so that no fence enclosure is needed. Of course, the grounding bus and enclosure frame of the substation must be connected to the building grounding system, whether or not the local grounding electrode system is installed. Outdoor portable heavy-duty equipment. This area usually involves such equipment such as power shovel, drag lines, mine installation. It presents one of the more difficult problems in avoiding dangerous electric shock voltage exposure. The mobility of the utilization equipment and frequently of portable power equipment precludes installation in a localized ground mat, such as would be employed at a fixed location. A safety ground system is utilized to ensure adequate grounding and personal safety. Both AC and DC equipment can be employed. For utilization voltage greater than 1000 volt, the objective is to limit the maximum equipment frame potential to 100 volt or less during the ground fault condition by selecting the grounding resistor in the substation. This picture relates to application where portable power center is connected to distribution, implying that utilization equipment is operating at lower voltage than distribution. The power transformer configuration is selected to separate ground fault condition in the utilization portion from distribution. The pickup of all the ground fault relay is typically set at 40% of the established ground current limit. For a ground current limit vary as to application and system voltage. For utilization equipment less than 1000 volt, maximum ground current limit must be 25 ampere or less. But common practice is 50 ampere. The 100 volt maximum frame potential limit applies to surface or underground utilization equipment greater than 1000 volt. This frame potential includes that which might be developed across grounding conductor to the safety of ground. Regardlessly, a ground current limit from 15 ampere to 25 ampere is typical. An exception to the preceding ground current limit is found in the underground grassy mine for phase mining equipment. In long wall mining have been towards 2400 watt or 4160 watt utilization. Maximum ground fault current must be limited to 6.5 ampere to 3.75 ampere respectively. Maximum ground fault relay pickup is again 40% of the current limit, and potential relying about the grounding resistor backup equipment are using 625 milliampere ground current limit and are successfully employing a ground fault relying pickup at 90 milliampere for primary protection. All equipment grounding for interior wiring system, all equipment grounding in designs for installation within building should be recognized, confirmed the minimum requirement of NEC. Basically, NEC design minimum acceptable limit for safety that may not be adequate for a particular application and may not necessarily provide for an efficient or practical use of high technology utilization equipment. The minimum requirement should be expanded in a more conservative direction as far as a system designer consider appropriate based on specific project. Interior unit substation and switching center. Switching center of modern vintage will be a part of the integral factory design metal enclosed equipment. The following two grounding error appear quite often, which are metal raceway for cable tray are not recognized as an electrical conductor, and no connection is made by the stub and extending into equipment enclosure. The grounding leads from a raceway is thought to be needed as a static drain, and is connected to ground bus with only 4 mm conductor. Termination of raceway system to the equipment enclosure can prevent burnout at the connection of sheet metal panel to each bolt sheet and minimizing the risk of serious damage to the equipment and injury to personnel.
Assalamualaikum. My name is Shazreen binti Shamsurija. Today I would like to talk about the Green Book, and my part is static and lightning protection grounding. Fundamental causes of static electricity. In a neutral or uncharged body, the electrons, negative components of the atom, and the proton, positive components, are present in exactly equal number. Static electricity is generated by the movement of electrons, which occurs when unlike materials are in contact with each other and are then separated. When two unlike materials are in intimate contact, electrons from one material move across the interface to the surface of the other, and their counterparts in equal number remain on the other body. An attractive force is thus established as equilibrium is achieved. When bodies are separated, electrons produce electrical charges on the object separated, which shows an increase in voltage between the two surfaces. Condition affecting the production of static charges depend mainly on the following. Firstly is the material characteristic. One of the material or substances must have higher insulating properties than the other to at least some degree to generate a static charge between them. The physical form may be solid, liquids or gases. The second one is the speed of separation. As the speed of separation of two substances is increased, the chance for impounding the charges on the material also increases, thus increasing the voltage difference between them. The third one is the area in contact. Larger contact area means that more charge may be transferred from one substance to the other, though the charge density may be the same. The fourth one is the effect of motion between substances. In the process of rubbing, more peaks on the surface are brought into contact, since surfaces that are smooth and flat to the eye are microscopically rough with peaks and valleys. And the electron travel only where actual contact occurs. Also, heating due to friction is the transfer of electrons. And lastly is the atmospheric condition. Condition required for a static charge to cause ignition. In order for a static spark to produce ignition in a combustible vapor and air mixture, there must be a sufficient energy stored in a charged body. The amount of energy that is stored from a capacity type discharge can be calculated by this formula. C is for the capacitance in picofarads, V is the voltage in volts, and E is for the energy in millijoules. Approximate values of capacitance in picofarads of some object are as follows. Human being is from 100 picofarad to 400 picofarad. Automobile is 500 picofarad. Tank truck 2000 gallon is between 1000 picofarad, and 3.6 meter or 12 feet diameter tank with insulated lining is for 100,000 picofarad. The energy necessary for ignition is dependent on several variables. Firstly is shape and spacing of the electrodes between which the spark occur. Second one is the composition of the gas mixture. The third one is the gas temperature, and the fourth one is pressure. Tests have shown that 0.25 millijoule stored energy is required to ignite an optimum mixture of saturated hydrocarbon gas and air, but where the voltage differences are less than 1500 volt and capacitance is less than 222 picofarad, the resulting sparks are unlikely to cause ignition of such a mixture because the energy developed is less than 0.25 millijoule. Acetylene gas used in industrial plants for cutting metal is exceptionally flammable. It needs only about 0.02 millijoule of spark energy to ignite. Measurement and detection of static electricity. Measurement of static electricity will have different magnitudes of electrical quantities than from power electricity. So techniques and instruments used for the measurement and detection of static electricity are different. Devices used in measurement and detection are, firstly is the electrostatic voltmeter. Electrostatic voltmeter are available in several ranges from 100 volt to 5000 volt. Operate on the principle of electrostatic attraction between movable and stationary metal vanes. No current is passed to maintain deflection. Portable, moderately expensive, fairly sensitive, do not indicate polarity. For the second one is neon lamp tester, inexpensive and quite sensitive. It will light up feebly when one terminal is grounded in the hand and the other makes contact with the charged body that carries a charge potential of 100 volt or more. Adjustable, series parallel grouping of neon lamp. Small capacitors can be arranged to give approximate quantitative information. For the third one is the solid state electrometer. It have very high input impedance so as to limit current drain 1015 ohms. Uses battery, so it must be switched on before entering a charged area and switched off after leaving the area. And lastly is the electrometer amplifier, used for the investigation of static electricity in the field and laboratory. High resistance in the input circuit and thus has low current drain. Used as a voltmeter, a charge meter and a current meter. Quite sophisticated and expensive and need experienced operator to use it. Method of static control. Static electricity generation cannot be prevented, but it can be controlled by providing means of recombining separated charges as rapidly as they are produced and before sparking voltage are attained. Method uses included the following. I will explain at the next page. So this is the grounding and bonding. Static problem can be solved by bonding the various parts of the equipment together and grounding the entire system. As you can see, it's the last one. Bonding, connecting the two objects together, minimize voltage differences between conductive objects, thus preventing sparking between the two bodies. This is the one in the middle. insulated wire 6 AWG or 4 AWG for mechanical strength. Current is on the other of microampere, 10 to 6 amp. Any ground adequate for power circuit or lightning protection is adequate for protection from static electricity. Even a ground resistance of 1 mega ohm is adequate for static grounding. Grounding, however, is not a cure for all the static problem. For example, if the material being processed is rather bulky and has a high dielectric characteristic, a static charge on the upper portion of the material is usually very effectively insulated from the ground, and it may result in a spark discharge. In case of processes involving non-conducting materials such as paper, cloth or rubber, it is not possible to drain off the static electricity charge by ordinary grounding and bonding. Also, charges on the surface of low conductivity liquids such as most refined petroleum product, these charges cannot be removed by bonding or grounding. In such cases, other methods of control such as ionization or humidification should be utilized. For the second one is the humidity control. The higher the humidity, the greater the conductivity. Example, the surface conductivity of plate glass at 50% relative humidity is about 1000 times its conductivity at 20% humidity. At normal humidity, 30% or more, an invisible film of water provides an electrical leakage path over most solid insulating bodies and the clothes and shoes of a worker, which drains away static charges as fast as they are generated. When relative humidity is 30% or less, the same materials dry out and become good insulator. In some cases, localized humidification by steam injection near the point where static electricity is accumulating has proved without increasing the humidity in the whole area. The minimum value of relative humidity is required for effective control of static electricity is difficult to determine and will vary with the process and the surrounding condition. However, it is believed that where the relative humidity is maintained in the range of 60% to 70% at ordinary indoor temperature, static accumulation are not likely to reach dangerous proportion. For the second one is the humidity control. The higher the humidity, the greater the conductivity. Example, the surface conductivity of plate glass at 50% relative humidity is about 1000 times its conductivity at 20% humidity. At normal humidity, 30% or more, an invisible film of water provides an electrical leakage path over most solid insulating bodies and the clothes and shoes of a worker, which drains away static charges as fast as they are generated. When relative humidity is 30% or less, the same materials dry out and become good insulator. In some cases, localized humidification by steam injection near the point where static electricity is accumulating has proved without increasing the humidity in the whole area. The minimum value of relative humidity is required for effective control of static electricity is difficult to determine and will vary with the process and the surrounding condition. However, it is believed that where the relative humidity is maintained in the range of 60% to 70% at ordinary indoor temperature, static accumulation are not likely to reach dangerous proportion. Okay, for the ionization, in the process of ionization, electrons are separated from the molecules. The electrons are negatively charged and the molecules that have lost them become positive in polarity. When a charged object is brought in contact with ionized air, the static charge is dissipated. The charge is either conducted to ground through the ionized air, or the charged object attracts a sufficient number of positively or negatively charged ion from the air to neutralize it. Ionization of air can be obtained by flame, alternating electric field generated by a high voltage supply, ultraviolet light, or radioactivity. This can be achieved by several devices and methods. The most common one is the static home, inductive neutralizer, electrical neutralizer, radiative neutralizer, and open flames. For the next one is the conductive floor. The use of conductive floor or floor covering may be required to prevent the accumulation of static charge. By grounding the personal and conductive object together, human body in a dry location can accumulate a dangerous static charge. Where such flooring is required, it should be of non-sparking material such as conducting rubber, lead, or other conductive compounds. The resistance of the floor should be less than 1 mega ohm when measured between two electrons placed 0.91 meter or 3 feet apart anywhere on the floor. In addition, to protect personnel against electric shock hazard, the resistance of the floor should be more than 25 kilo ohm when measured between an electron electrode placed at any point on the floor and a ground connection, and between two electrodes placed 0.9 meter or 3 feet apart at any point on the floor. For the next one is conductive footwear and caster. When conductive flooring is used, operator entering the area must wear conductive non-sparking footwear. Mobile equipment should make contact with the floor directly or through conducting rubber caster. Shoes tester are available for determining the resistance while the shoes are being worn. Such testers are essentially direct reading ohmmeter with resistor to limit the short circuit current to 0.5 mA. The resistance between the wearer and ground must not exceed 1 megaohm, which is the total resistance of the conductive footwear on a person plus the resistance of the floor. Okay, for the special precaution, providing wearing apparel with low static producing qualities, establishing rigid operating procedure, using conductive rubber mats where conductive flooring is not used throughout an area, and lastly is the proper maintenance. Determine if all bonding and grounding connections are intact. Ascertain the resistance of all equipment to ground. This may be found by the use of commercially available ohmmeter. A resistance on the order of 1 megaohm is usually satisfactory for static mitigation. Test belt to see if they have maintained their conducting characteristic. Take resistance measurement of conductive flooring. Take instrument reading to determine if static charges are accumulating either because of the loss of one of the static control device or because of the charge in operating conditions such as machine speed, the addition of material handling equipment, or use of new material that may have different characteristics. Hazard in facilities and mechanism. Okay, this is for the belted drives. Most power belts and conveyor belts are constructed of insulating material. These are pressed into contact with pulleys and idlers and generate static electricity at the point where the belt separates from the pulley. The generation of static electricity increases as speed increases or humidity decreases. Rubber or leather flat belts running at moderate or high speed may generate sufficient static electricity to produce spark. Wheel belts are not susceptible to hazardous static generation as are flat belts. Conveyor belts used for the transportation of solid material usually move at low speed and usually do not produce static electricity. When conveyor belts carrying heated or dry materials are operated in a heated atmosphere or move with high velocity, static generation might be significant. In locations where static charges are a real hazard, consideration should be given to direct or gear drive rather than belted drive. If belt drive must be used, the following method of static control should be used. Firstly, a grounded static control collector is installed. Second, a belt of conductive material is used. And lastly, special belt dressing are applied. Okay, this part is for the lightning protection grounding. Lightning is the discharging of high voltage charge cell within clouds to each other or to the earth. The cloud to ground or CG charge cell in cloud normally attract charges of opposite polarity on the earth surface or on high object located directly below them. When the cell charge reach a critical level, when the insulation between cloud and earth breaks down, it develops a step ionized path resulting in a high current discharge or stroke that neutralized for the moment this cloud and earth charge. The discharge current increases from 0 to a maximum in usually from 1 microsecond to 10 microsecond and then declines to half the peak value of 20 microsecond to 1000 microsecond. Lightning flashes usually consist of sequence of individual return stroke that transfer significant electrical charge usually from the cloud to earth. The original rather slowly developing stroke is followed on the average by 2 to 3 subsequent stroke but may contain as few as 1 and as many as 20 strokes. Each stroke has been found to contain peak current in the range of 2 kA to 300 kA and has a nominal duration of 20 microsecond to 50 microsecond. For most flashes, the subsequent stroke, that is strokes that occur after the first stroke, will contact the earth at the same stroke point as the first stroke because they travel through the same charge channel that was established by the first stroke. However, nearly one half of all the flashes can contain stroke with different ground stroke point. They can be separated by a few hundred meters to several kilometers. National Lightning Detection Network. Starting in 1989, An objective means of measuring lightning was initiated. The NLDN, also known as the National Lightning Detection Network, is a configuration of remote field sensors that are employed to detect radiated electromagnetic signal from lightning discharge. The Electric Power Research Institute, EPRI, from the network in a joint venture with Global Atmospheric (GAI), presently owned by the Vaisala Inc. This Arizona-based company continues to operate the NLDN. Most importantly, lightning data is now recorded in real time via a satellite connection. The expected flash detection efficiency range between 80% to 90%, varying slightly by region. Validation of the performance has been reviewed based on multi-camera video studies of storm in New York and on rocket-triggered lightning measurement in Florida. Interested parties are able to access lightning information, archive or real-time from GAI. The information available gives users the ability to verify lightning activity for precautionary action, backup generation or safety, or forensic diagnostic application. Lightning parameters available include the following: latitude, longitude of individual lightning ground contact points, Greenwich Mean Time and date, peak amplitude of event, polarity of discharge, multiplicity. Standard and custom design products are available to reflect average annual lightning densities for use in protection and design application. The ambiguities of thunderstorm days have been replaced by statistically valid 7-year average and are available for domain as small as 48.3 km times 48.3 km. For site-specific investigation, root mean squared accuracy of 500 meter should be anticipated, with individual qualities and position parameters provided for each stroke as necessary. For the next slide is the lightning protection method. This is the Franklin air terminals and Faraday cage. With Franklin air terminals and the connecting across conductors and the down conductors, our Faraday cage exists. You can see on this one and this one. It's produced Faraday cage. The Franklin air terminal and the Faraday cage are combined to form a complete system. Referred to by several terms air terminal system, Faraday cage or the Franklin method or the fortress concept. Steel frame structure adequately grounded meet the preceding requirement with the addition of air terminal. The air terminal are spaced 6 meter to 7.5 meter apart on the edge of the structure and 15 meter on the interior of the roof. Cross connection are made at 45 meter. Without a steel framework, down conductors must provide at least 2 paths to earth for a lightning stroke to any air terminal. The second one is early emission ionizing streamer. Early emission and ionizing streamer lightning protection devices are considered dynamic devices compared to the Franklin cone or the Faraday cage. Radioactive sources are used to obtain ionization of the air around the tip of the air terminal. The theory states that the radioactive ionization terminal produces a rising air stream. This column acts as an extended air terminal, reducing the tension, or if the potential is sufficient, a conductive streamer is provided. The system has not been universally accepted by the scientific community. Although controversial, the system is being sold throughout the world, especially in France. And lastly is the rocket. Rockets have been and are being used to discharge under controlled condition charged thunderclouds. The firing of rocket with a short trailing conductors can result in the charge within the cloud being discharged. Usually the lower portion of the cloud is negatively charged, with the upper portion of the cloud positively charged. With a trailing conductor, the charge can be directed to an object. Testing of explosive storage building using this method showed the reinforcing bars and the concrete dissipated the majority of lightning stroke instead of the driven ground roads and the ground loop. And for the practices for lightning protection is building and structures involving hazardous liquid gases or explosive require additional protection. In this, it is highly desirable to keep the stroke current away from the structure, not even utilizing its metal skin or framework as a down conductor. For such cases, including tanks farm and explosive manufacture and storage, a separate diverter protection system is employed. The diverter element consists of one or more masts or one or more elevated wire between masts or poles, meeting the requirement of lightning protection. For structure containing flammable liquid and gases, the radius of the sphere of protection reduced to 30 meter instead of the 45 meter dimension normally used. To prevent the side flash, the minimum distance between a mast or overhead ground wire and the structure to be protected should not be less than the side flash distance.
54 can continue about grounding and bounding National Electrical Code NEC Article 250. This is a scope of our article. You can see what system and equipment are required to be grounded, location of the grounded connection, type of electron and size of grounding and bounding connector, and method of grounding and bounding. This is overall of the NEC Article 250. They will divide for several parts, and this is severity of electric shock. The severity of electric shock is related to the three elements. If the combination of these three elements is just right, the shock can be severe or lead to the electrocution. That element is first amount of current, length of the time current is present, path of current through the body, frequency of the current. Amount of time current is allowed to be passed through a body. This is effect of electricity on the woman. The scale of the effect electricity. It maybe does not take much current to the cause injured, but will lead to the cause die. This is a series and parallel pair of current. Okay, definition. Bounding jumper, supply side. The conductor on the supply side of the service or separated device system over current protection device that ensure electrical conductivity between two metal and the grounded conductor. We can see from the figure we can see the conductor on the supply side of the service over current protection device that ensure electrical conductivity between two parts required to be connected. We can see from the first figure and other figure. The conductor on the supply side of the SDS over current protection device that ensure electrical conductivity between two parts required to be electrically connected. And next, performance requirement for the grounding and bounding. DS two for grounding and also for ungrounding. For the grounding, we can see for electrical system grounding. Electrical systems are grounded, connected to the earth to limit the voltage induced by lightning, line surge of intentional contact by higher voltage line. System grounding had reduced fire in the building as well as voltage stress on the electrical installation, trebly ensuring longer installation life for motor, transformer and other system components. To limit impulse voltage, the grounding electron connector should not be any longer than necessary, and unnecessary bend and loop should be avoided. Second, equipment grounding. Metal part of electrical equipment are grounded to reduce engine within the building or structure from inducing voltage for indirect lightning strike. Failure to the ground metal part to the earth can result in inducing voltage on the metal part from an indirect lightning strike, seeking a pain to the earth within the building, possibility resulting in a fire and or electric shock from the side flash. Third is equipment bounding. Metal part of electrical race rail, cable, enclosure, and equipment must be connected to the supply source via the infected ground fault current path. To quickly remove dangerous voltage on the metal part from a ground fault, the effective ground fault current pair must be substantially low impedance to the source, so fault current will quickly rise to a level that will open the branch circuit over current protection device. And this is a for current calculation. We can see from the picture it have 583 ampere. The 100 ampere overcurrent device quickly open and remove dangerous voltage from the metal part. Number 4 is a bounding connective material. The time it takes for the overcurrent protection device to open is depend on the magnitude of the fault current. A higher fault current value will result in a shorter clearing time for the overcurrent protection device. For example, a 20 overcurrent protection device with an overload of 40 ampere to times the 20 ampere rating take 25 to 150 seconds to open. The same device at 1 ampere, 5 times the 20 ampere rating, 3 in 5 to 20 seconds. Effective grounded fault current pin. Metal part of electric rail cable ensure equipment must be bonded together and to the supplies source in the manner that created a low impedance path for grounded current that fertilize the operation of the circuit over current protection device. To ensure a low impedance ground fault current path, all circuit conductor must be grounded together in the same rail cable or trace. We can see from the picture, all the cable we ground together. Because the earth is not a low impedance path for a fault current and is not suitable to serve as the requirement effective ground fault current pin. Therefore, an equipment grounding filter for type organized in 250.118 is required to be installed with all circuit, as we can see for the picture. And this is a ungrounded system. Ungrounded system are those systems with no connection to the ground or to the connective body that extend the ground connective to the ground connection. For equipment grounding, major part of electrical equipment are grounded, connected to the earth to reduce induced voltage on a metal part or from lightning, so as to prevent fire from the earth within the building. This is equipment bonding. Metal part of a rail cable enclosure or equipment must be bonded together in the manner that created a low impedance path for a ground fault current to fertilize the operation in the circuit over current protection device. The fault current path must be capable of safely carrying the maximum grounded fault current likely to be imposed on it from any point of the wiring system should a ground fault occur to the electrical supply source. This is a bounding connective material. Conductive materials such as metal water piping system, metal sparkler piping, metal gas piping, and other metal piping system, as well as exposed structures, steel member likely to become energized, must be bound together in a manner that correct a low impedance current fault current bit that capable of carrying the maximum fault current likely to be imposed on this fault current bit. Electrical equipment, wiring, and other electrically conductive material likely to become energized must be installed in a manner that creates a low impedance fault current pin to fertilize the operation of overcurrent protection device should a second ground from a different phase occur. The overcurrent device open because of a line-to-line short circuit for the first ground fault and the second ground fault. This is a requirement. Electrical system grounded system that are grounded should be connected to the earth in a manner that will limit the voltage imposed by lightning line circuits of international contact with high voltage line and that will stabilize the voltage to the earth during normal operation. Second, grounding of the electrical equipment non-current carry conductive material enclosing electrical conductor or equipment or forming part of a such equipment shall be connected to earth so as to limit the voltage to ground on that all material. The bounding of electrical equipment non-current carry conductive material includes electrical conduct of or equipment or forming part or such equipment shall be connected together and to the electrical supply source in a manner that establish an effective ground fault current pin. Bounding of electrically conductive material and other equipment electrically conductive material that are likely to become energized should be connected together and to the electrical supply source in a manner that establish an effective grounded current pin. And the last, electrical ground fault current pin electrical equipment and wiring and other electrically productive material likely to become energized and should be installed in a manner that created a permanent low impedance circuit to fertilize the operation of the overcurrent device or ground detector for high impedance grounded system. It shall be capable of safely carrying the maximum ground fault current likely to be imposed on it from any point of the wiring system where a grounded fault may occur to the electrical supply source. The earth should not be considered as an effective ground fault current pin. For the requirement 1 and requirement 2, grounding issue that specifically refer to connection to the earth. Requirement 1 is a system grounding on internal connection of the system connector on the grounded system to the earth. The state purpose of the international connector to the earth is.
Okay, we continue in Article 250 with section 0.6 about objectional current. Okay, this section is about on how to prevent objectional current, temporary current not classified as objectional current, and the limitation to permissible alteration. Why we have to prevent objectional current? Because we want to avoid fire, electric shock, or improper operation of circuit overcurrent devices. Okay, why temporary current not classified as objectional current? Because these temporary currents came from abnormal condition such as ground fault. Okay, the limitation of objectional current is if the current introduce noise in electronic equipment, that current also not considered as objectional current. Therefore, this circuit must be connected to an equipment grounding conductor. Okay, this is an application of objectional current due to improper neutral connection. Okay, the violation, where is the violation? Okay, because we improper do the neutral connection, okay, the current flow neutral to case on the load side of the service equipment. So that's why we call objectional current. Okay, in Article 250 Section 24 about service equipment. Okay, service equipment from a grounded system must have the neutral conductor grounded. Okay, this is the application. The application is about multiple disconnect neutral conductor required. Okay. Service neutral conductor at each service disconnect. We must install service neutral conductor at service disconnect. Okay, we also have to install neutral to case connection at each disconnect. Okay, the neutral conductor must be run to and connected to each service disconnect via a main bonding jumper. Okay, in Article 250 Section 24 about service grounding connection, okay, we have three main. First, a grounding electrode conductor must connect the neutral conductor to a ground electrode at the service drop. Second, meter enclosure. Third, service disconnect. Okay, in Article 250 Section 50 about grounding electrode system, okay, metal building frame, metal water pipe, concrete encase, ground ring, road pipe, and other metal structure can be used for grounding. Okay, grounding electrode required to be used to form the grounding electrode system where present. Include electrode that are an inherent component of the building construction. By inception, concrete encase electrode not required to be used where doing so involve disturbing concrete footings of existing structures or buildings. Okay, the minimum distance between two roads is 6 feet apart or follow manufacturer instruction. Okay, this is on how to do the grounding, the example on how to do the grounding. Okay, in section 2, in article 250 section 32b, okay, the article shows about grounding method 1. Okay, we have two service building at building 1 and at building 2. Okay, building 2 is solid grounded conductor. The both service equipment grounding conductor require grounding electrode. Okay, that's all from us. Thanks.